Ever wondered how the food you eat, the air you breathe, or the water you drink is safe and healthy? Analytical chemistry holds the answer. This field, a cornerstone of science, is all about identifying what things are made of and how much of each component is present. It's the detective work of the chemistry world, shedding light on the composition of everything around us. From the medications we take to the environmental pollutants we aim to decrease, analytical chemistry is pivotal in our daily lives. It's divided into two main branches: qualitative analysis, which identifies what substances are present, and quantitative analysis, which determines how much of those substances are present. These fundamental aspects make up the bedrock of analytical chemistry, helping us make sense of the complex chemical world we live in. Now, let's delve deeper into the two main types of analysis. Analytical chemistry is all about the what and the how much. Let's delve a little deeper into that. When we talk about the what, we're referring to qualitative analysis. This is where we identify what substances are present in a sample. Picture yourself as a detective, using your keen observation skills to determine what elements, ions, or compounds are present in a mysterious substance. But unlike a detective, you're not looking for fingerprints or footprints. Instead, you're looking for the unique chemical fingerprints that each substance leaves behind. These might be things like color changes, precipitates, or even the production of gas. Now, once you've identified what substances are in your sample, you might ask, how much of each substance is there? That's where quantitative analysis comes in. It's all about measuring the exact amount of a substance in a sample. It's like being a baker, carefully measuring out each ingredient to ensure your cake turns out just right. But here's where it gets interesting. There are different types of quantitative analysis. We have gravimetric analysis, where we measure the mass of a substance; volumetric analysis, where we measure the volume; and instrumental analysis, where we use various instruments to measure properties like absorbance, emission, or conductivity. Each type of quantitative analysis has its own set of tools, techniques, and procedures. Just like a carpenter has different tools for different jobs, an analytical chemist uses different types of analysis depending on what they need to measure. So you see, analytical chemistry isn't just about knowing what's in your sample, it's also about knowing how much is there. It's a fascinating field that combines the best of detective work, baking, and carpentry, all wrapped up in a lab coat. Having understood the basics, we must now look at some key terms and concepts used in the field of analytical chemistry. So stick around, because we're just getting started. Ever heard of the terms normality, molarity, and molality? Let's decode them. In the realm of chemistry, these terms refer to ways of expressing the concentration of a solution. Normality, denoted by the letter N, is a measure of concentration equal to the gram equivalent weight per liter of solution. Gram equivalent weight is the measure of the reactive capacity of a molecule. So, when we say a solution has a normality of 1, it means it has 1 gram equivalent of solute per liter of solution. Similarly, molarity, represented by M, is another way of expressing concentration. It's defined as the number of moles of solute per liter of solution. A mole is a unit used to express amounts of a chemical substance based on the number of atoms in 12 grams of carbon-12. Then we have molality, represented by a lowercase m. This is the number of moles of solute per kilogram of solvent. Unlike molality isn't affected by changes in temperature or pressure because it's based on mass, not volume. Next is the mole fraction, which is the ratio of the number of moles of a component to the total number of moles of all components in the mixture. It's a dimensionless quantity, and its value is always between 0 and 1. Moving on to molecular weight, it's the weight of a molecule based on the atomic mass units of its atoms. The atomic mass unit is a standard unit that is used for indicating mass on an atomic or molecular scale. Equivalent weight, on the other hand, is the mass of a substance that can combine with or replace 1 mole of hydrogen. It's used in equations involving acids, bases, or redox reactions. These concepts are crucial in understanding the concentration and strength of solutions, which we'll explore next. Ever wondered how chemists determine the strength of a solution? Let's find out. When we talk about the strength of a solution in chemistry, we're referring to its concentration, how much solute is dissolved in a certain amount of solvent. This can be expressed in various ways, such as molarity, molality, normality, and mole fraction. Molarity, denoted by M, is the number of moles of solute per liter of solution. It's a highly common measure due to its direct relation to the solution's volume. Molality, on the other hand, symbolized by M, is the number of moles of solute per kilogram of solvent. Unlike molality doesn't change with temperature because it involves mass, not volume. Now let's talk about normality, denoted by N. It's a measure of the number of equivalent weights equivalents of solute in 1 liter of solution. Equivalent weight is the mass of a substance that can combine with or replace 1 mole of hydrogen. It's used in acid-base, precipitation, and redox reactions. Last but not least, we have the mole fraction, represented by X. It's the ratio of the number of moles of a component to the total number of moles of all components in the solution. It's a dimensionless quantity and, like molality, is not temperature dependent. Understanding these measures of concentration is crucial because they directly impact a solution's effectiveness. For instance, in a chemical reaction, the rate can be influenced by the concentration of the reactants. Similarly, in a medicinal context, the effectiveness of a drug can be determined by the concentration of the active ingredient. These concepts are not just theoretical, they are applied in practical scenarios every day, from the lab to the pharmacy, and even in the food and drink industry. Now that we have a solid understanding of these concepts, let's move on to primary and secondary standards. Scene script. Primary and secondary standards play a vital role in analytical chemistry, but what exactly are they? Dive into the world of standards with us. In analytical chemistry, standards are the yardsticks that allow us to measure the amount of a substance in a given sample. They fall into 2 categories: primary and secondary standards. Primary standards are the gold standard, the crème de la crème of measurement. They're pure substances with known properties, which we can measure directly. They're stable, they don't react with air or water, and they're easy to purify. Sodium chloride, for example, is a primary standard. We can weigh it, dissolve it, and use it to calibrate our instruments. But what about secondary standards? They're a step down from primary standards, but no less important. These are substances that we can't measure directly. Instead, we determine their properties by comparing them to a primary standard. They might react with air, they might not be perfectly pure, but they're still useful. Hydrochloric acid is a secondary standard. We can't weigh it directly, but we can compare it to a primary standard to determine its concentration. You might wonder, why do we need 2 types of standards? The answer lies in practicality. Primary standards are ideal, but they're not always feasible. They can be expensive, hard to handle, or simply not available. That's where secondary standards come in. They're more practical, more accessible, and they allow us to measure a wider range of substances. So primary and secondary standards are the dynamic duo of quantitative analysis. They play off each other, each with their own strengths and weaknesses, to give us the most accurate measurements possible. They're like the Sherlock Holmes and Dr. Watson of analytical chemistry, solving the mysteries of chemical composition. These standards ensure that we can reliably measure substances, a critical aspect of analytical chemistry. So, we've taken a whirlwind tour of analytical chemistry today. We dove into the heart of this fascinating field, exploring how it helps us understand the world around us. We've seen how qualitative analysis allows us to identify what substances are present, while quantitative analysis quantifies the amount of these substances. We delved into the fundamental concepts of normality, molarity, molality, mole fraction, molecular weight, and equivalent weight, understanding how they each play a crucial role in expressing the concentration and strength of solutions. The importance of primary and secondary standards in ensuring accuracy and precision in our analyses was also highlighted. Each of these elements work together to form the backbone of analytical chemistry. The knowledge of these concepts and their applications is not just confined to chemistry labs, but extends to various fields including medicine, environmental science, and forensics. Thanks for joining this journey into analytical chemistry. Subscribe for more because you won't find me later.